Let us look at proposition number 14 of book 10 of Euclid's Elements. Now, here in this particular proposition, uh, before the actual proposition, there is a lemma. Like, a lemma is basically something that has to be proved uh, to simplify the main proposition. Okay, so let's see what this lemma says. Given two unequal straight lines, to find by what square on the greater is greater than the square on the less. So it seems a little bit tricky, right? So let's see. We are given two unequal magnitudes A, B, and C. And what we have to do is figure out AB square minus C square is what square. So how do we figure out what square? So now here what we do is we draw a semicircle first on AB, on the greater magnitude. Then at A, we draw a circle of radius C and we take the intersection point and we join AD and we join BD. Now we don't want this circle, so let's hide that. Now here AB square minus C square is required. But remember, AD is equal to C. So AB square minus C square, that is AD square. Does this remind you of something? Yes, Pythagoras theorem, because angle ADB is going to be a right angle. Why? Because it is an angle subtended by the diameter of the circle. So, which means AB square, which is the hypotenuse, is equal to AD square plus BD square. If we move it around, we get AB square minus AD square is equal to BD square. So, which means AB square minus C square is equal to BD square. So, the third side of this triangle will give us the answer to this question. So, this was the lemma. Let's get to the main proposition. If four straight lines are proportional and the square on the first is greater than the square on the second by the square on a straight line commensurable with the first, then the square on the third is also greater than the fourth by the square on a third line commensurable with the third. Quite a mouthful, but the proposition doesn't end there. And if the square on the first is greater than the square on the second by the square on a straight line incommensurable with the first, then the square on the third is also greater than the square on the fourth of the square on a third line incommensurable with the third. Quite a big description of the proposition. Let's see what it means and how to prove it. We are given magnitudes A, B, C, D in proportion. So that means A is to B is equal to C is to D. And the proposition says that A square on A is greater than the square on B by a given magnitude square. Square on the third magnitude. Again, the proposition says with respect to C and D, the square on C is greater than square on D by the square on another given straight line. This is what we are given. Now, what do we have to prove? We have to prove that if A is commensurable with E, then so is C with F. And if A is incommensurable with E, then so is C with F. Let's take it step by step. Now, A is to B is equal to C is to D. We are given that. Now, that implies that A square is to B square is equal to C square is to D square. The squares will also be proportional. Now here, if you notice, we are given that a square is greater than b square by e square. That means b square plus e square is equal to a square. And similarly, c square is greater than d square by f square. So that means d square plus f square is equal to c square. Now we substitute a square and c square with this. We get b square plus e square is to b square is equal to b square plus f square is to d square. So we have substituted a square and c square with these two. This is the sum, this is the sum. So taken separately, we can write it as e square is to b square is equal to f square is to d square, and which means e is to b is equal to f is to d. Now let's invert it. So inversely, b is to e as d is to f. Now here a is to b and b is to e, c is to d, d is to f. So that means we can combine them and write it as a is to b is to e is equal to c is to d is to f. And x equally we can write it as a is to e as c is to f. And what does this proportion mean? It means if a is commensurable with e, then so is c with f. And if a is incommensurable with e, then so is c with f. So here, where did we use the lemma? Here, a square is greater than b square by e square. So to get this e square, we use the lemma. Similarly, to get the f square, we use the lemma. So that was proposition number 14 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.